The broadcast is now starting. All attendees are in listen-only mode.
Well, hello everyone and welcome to today's showcase webinar. My name is Christina Lanham and I'm going to be moderating a bit today. As you can see, our session is Boom Hoist Wire Rope. Our host, as always, is Mike Parnell, Technical Director of ITI, and we have a guest presenter, Don Pellow of Pellow Engineering Services. And before we get started, I'm just going to run through a couple of housekeeping items here. For those of you who don't know, ITI is a technical and business company that we work toward the common goal of being the go-to authority on safe crane rigging and load handling operations. And we've been blessed to work with some of the amazing organizations you can see on the screen. And we've taken a great deal of pride in working with them. You can see just a little bit from the companies we worked with. We work with a number of different industries, and we provide a lot of practical hands-on training for them. Here's just a quick overview of some of the trainings that we do offer. We offer everything from basic rigging applications up to lift planning and crane management. And if you get a chance, we'd love for you to get onto our site at iti.com/training and check those out. And within our company, we have a number of different divisions. We have our hands-on training, online training, we have a technical bookstore, we offer field services for manual development and accident investigation. We have workshops that we hold around the country, as well as the webinars that you guys are on now. And again, Mike Parnell is your host. He is the founder and technical director of ITI, and he spends quite a bit of his time volunteering with ASME and serving on those committees.
I'd like to say hi, Christina. Thanks for everybody joining us today, and we look forward to a terrific presentation by Don. He's certainly an expert in the field of wire rope and rigging activities and applications, and it should be a really good webinar. So I'm looking forward to it myself. So I'm going to be right along right with you all the way through. Thanks, Christina.
Not a problem, Mike. And as mentioned today, our guest presenter is Don Pellow. He has over 35 years of experience in the wire rope and rigging industry. After serving on several high-level positions at Wireco World Group, he now operates Pellow Engineering Services, where he conducts field investigations, failure analysis, lab testing, and expert witness testimony, in addition to training and consulting services. And with that, I'm now going to give the mic and the screen over to Don, and he's going to start the presentation.
Thank you, Christina. Welcome to everyone, whether it's morning or afternoon. I welcome you, and thank you, ITI, for the opportunity of presenting this. As we go through this presentation, they mentioned that I do have my own company, and that's been founded back in 1994. Several areas I'm involved in is testing of wire rope, whether it be independent testing or litigation work as far as an expert witness. I do training as far as riggers, and crane operators. Also, I publish and distribute Bob's crane and rigging handbooks. Anyway, today we're going to really focus on cranes, and in particular, boom hoist lines. And about 2 years ago, I felt very compelled to write an article, to develop a PowerPoint presentation, and to get more information to the industry, the end user, distributors, OSHA people, trainers. Things are very important, and as I mentioned, boom hoist lines have become a very focused area for me because I have seen in the last 5 or 6 years some very traumatic accidents when boom hoist lines fail, booms come down, which has resulted in multiple deaths and horrible injuries to personnel. So as we get started here, as Mike mentioned, you have questions, we'll take those at the last, but I want to go through this boom hoist wire rope presentation and present some very detailed information which I have developed over the years, includes photographs, laboratory testing, field testing, and we'll get started now. Cranes. Construction cranes come in many forms, shapes, designs. As you see on this lattice truck boom crane, showing the auxiliary line to the left, and to the right you will see the boom pennant lines attached to the upper bridle configuration of sheaves, which then are attached to the lower bridle in an operating system of boom hoist wire rope. And this we're going to focus on because many times on a crane, this is the first wire rope that will wear and fatigue, and will be the first wire rope to break on a crane if all wire ropes are neglected as far as inspection and replacement. Looking at this extended boom with the auxiliary hoist and the extended boom, the luffing boom, we see the wire rope, the hoist line coming down, but to the right you'll see pennant lines, and these are stationary lines that do not operate over sheaves, and of course they fail in a different mode or wear out in a different mode than a hoist line. Let's review briefly the ASME B30.5 and 1926 retirement criteria of OSHA. And I focus on this for several reasons. We'll revisit this at the last, but currently the retirement criteria of wire rope is mostly all visual on cranes. 6 randomly distributed broken wires in one rope lay, or 3 broken wires in one strand. And over my years of experience, I do not see concentrated broken wires in one strand mostly. It's mostly randomly distributed broken wires in areas that operate over sheaves or on and off drums. Secondly, we address rotation resistant wire rope of wire ropes, 2 randomly distributed broken wires in 6 rope diameters, or 4 broken wires in 30 rope diameters. We're not going to focus on this today. The third bullet point, 1 outer broken wire in the valley at the contact point of the core. Next, wear of 1/3 the original diameter of the outer individual wires. As I explain in my training and presentations, it's very difficult, even as a wire rope engineer with 40 or 45 years experience, to judge whether the outer wire is worn 1/3 through its diameter. Actually, I try to refocus this on, let's go back to measuring the wire rope originally installed on a crane and focus on the diameter reduction. This is more of a actual objective evaluation instead of subjective. Next is kinking, crushing, bird caging, any kind of gross damage that distorts the rope structure that cannot be repaired. And of course, most of the time, the wire rope, when it is damaged, cannot be repaired. Evidence of heat damage, and this can be damage that's obvious by a blued section because of the heat treating of the wire due to heat damage, whether it be lightning, a torch, grounding of a torch. You may also see a rough schematic upon the surface of the wires if they're heat damaged, a bluing. The next bullet point, reduction in diameter of more than 5% of nominal. I briefly mentioned momentarily that it's important to know the original diameter of the rope that's installed on the crane after it has been run maybe 2 or 3 different operations through this entire cycle. I mention this because the current codes and standards in the industry allow the wire rope manufacturer to design and manufacture a wire rope up to 5% over nominal, down to 0%. And so it's important to know the original diameter to determine the amount of wear on that particular rope. So 5% of nominal may not really reflect the true wear on that rope. The next bullet point, in standing ropes, we're talking about pennant ropes that really do not operate over sheaves or drums. The retirement criteria is either 2 broken wires and 1 rope lay beyond the end connection, or more than 1 broken wire at the end connection. And briefly mention, I won't get into much detail on pennant lines, it's important to inspect the wire rope at the entrance into the socket or the end fitting. Many times these breaks are hidden at the interface of the socket and wire rope, or slightly inside the socket, so it's important to more or less flex the rope at this location. And of course, severe corrosion or pitting of the wires. I will show slides later on in this presentation indicating what severe corrosion is as opposed to light surface corrosion, which can be wiped and the wire rope relubricated. If you are online, I'm sure you are right now, if you have a pencil and paper, mark down these numbers. On load hoisting drums, the hoisting drums of the auxiliary hoist or main hoist, the minimum pitch diameter is 18 D over D. That is 18 times the diameter of the sheave or drum divided by the nominal diameter of the wire rope. On the traveling blocks, the sheaves can be manufactured and designed to a 16 D over D ratio, slightly smaller. One reason this is incorporated is that the smaller diameter sheaves will develop or enhance broken wires in the wire rope at that location as opposed to larger diameter. I have a very interesting chart I will show you later, which is very dramatic, that shows the vast difference in wire rope life and fatigue of even these two slight differences in D over D ratios. So again, mark this as 18 D over D, 16 D over D on hoist and main hoist lines. Now, of course, as we look at the wire rope, it's very important to choose the correct wire rope and to install it properly, where we have a nice evenly thread wind across the drum. And of course, we'll always have crossover points which produce and manufacture locations of possible damage where it crosses over. As we look at the actual point location of the boom itself, you can see the auxiliary hoist on the left, the sheave itself, the boom tip, and the point for a multiple wind or the main hoist line. These sheaves are very important because they must be on size to properly support the wire rope. They must be free to rotate, bearings must be good, and as I show later on, the inside surface of the groove must be the correct diameter, must not be damaged, and free of corrugation. Looking at the traveling block, and of course these sheaves can be down to 16 D over D ratio, smaller than point sheaves, which allows the operator or the oiler or the inspector to more or less detect fatigue breaks under normal wear at the traveling block location as opposed to the point, because they are slightly smaller. Here's a photograph of the wire rope that has undergone wear, fatigue breaks, and of course this rope has gone way beyond retirement criteria. It's in this location or this program to illustrate what idle wire looks like. You can see the flattening of the wire, and then eventually the wires will start to break up on the crown. This is normal type of wear, which is inspected for and will be experienced under normal operating conditions of a rope operating on and off sheaves. But let's focus on the boom hoist lines. What is different about these wire ropes and these applications as a boom hoist line different than the hoist lines? Why is it that these wire ropes in this location for boom hoist lines will wear out, fatigue, and possibly even break sooner than the other wire ropes on a crane? Looking at the upper bridle and lower bridle sheaves of a boom hoist system, you can see it's a multiple winding system, many parts of the line, as it operates on and off. Now, admittedly, the boom is not lowered and raised that many times during an operation, as opposed to the operation of a hoist line over a sheave. However, in this location, there's much more damage occurring here because of smaller diameter sheaves, which I will mention later on, because of vibrations that are impounded through the working of the boom itself, even not under load, just moving the boom with a load of the rigging, the ball, the hook, any below the hook lifting devices can impede vibrations or impact loading on this wire rope. And these vibrations are all dampened in the wire rope, and especially where they contact sheaves or end fittings. Again, even as the system goes, wire rope operates through the system of a boom hoist line, you'll see It can change direction. So we have reverse bending, which is another critical point, which decreases fatigue life of wire rope and leads to earlier fatigue breaks of the outer wires. Now, as I mentioned before, if we looked at the operating rope, we can have 18 DOD ratios on drums and 16 DOD ratios on shivs. However, focus on this. On the boom hoist drum, the minimum pitch diameter can go down to 15 DOD ratio, and the boom hoist shivs also the 15 DOD, which are smaller than the shivs or drums on a hoist line. Also, as we look at these boom hoist systems, the drum itself on the boom hoist line is usually positioned maybe in a more awkward position to inspect. It's usually a smaller shiv, smaller diameter drum, and also the width, flange to flange, seems to be smaller. So you get multiple wraps. The photograph above this, which shows this erratic winding, that rope is not under tension, but it can show what can happen if there's a loss of tension and the operator begins operating again with the wire rope not following a nice thread winding location. So damage can occur in this location. As we look from the cab, the base of the boom, upward on the boom itself, you can see the lower bale shivs, the upper bale shivs, you can see reverse bending, and there's multiple windings. Now, as you picture, as the boom is raised, these groups of shivs, the upper and lower shivs, come closer together, which increase the fleet angle. And as we look at the fleet angle, this is another situation to dramatize what can happen when the off-lead angle is too great. There's wear of the wire rope against the flange of the shiv. It could be against the edge of the drum, but damage can occur here. So it's important when inspecting wire rope that the shivs be inspected again for diameter, freedom, rotation, condition of the grooving, and also any wear on the side of the flanges that will decrease that width is an indication there has been excessive fleet angles. Looking up again, and we'll focus again on this upper bale shiv, it's floating. It has weight, could be several hundred up to 1,000 pounds, and as the machine is operated, as the crane goes through its operations, watch the bale shiv. If you're out in the field, watch, it'll flex up and down, it'll move. This produces vibration and impact loading, not only in the pennant lines that we see in the top left of the photograph, but throughout the system, the boom hoist lines to the bottom right. During inspection of boom hoist lines, this is particularly awkward or placed in an awkward position and is not as easily detectable as shivs in a traveling block, which can be easily obtained or accessed. These shivs more or less have to be inspected by hands-on, possibly with the use of a ladder or someone up on top of the cab. It's important to inspect these hands-on because many times a brief observation, which is done on a daily basis during a pre-lift operation, there are buccal wires which are not detectable from a distance. So it's important to have hands-on, and I always suggest, of course, using a micrometer or a caliper periodically, but on inspection, even during daily inspection, employ the use of a cotton cloth to rub against the wire rope. Many times the buccal wires are there, but they don't protrude from the surface, and so they're not observable from a distance. We'll get more into this as we go through this presentation. When boom hoist wire ropes break, unfortunately, when they break, something traumatic is going to happen. Fatalities, men and women are crushed to death. Riggers wind up maybe a paraplegic from a back injury. So let's take a look at some of the accidents which I've been involved in inspecting and analyzing over the last several years. Boom hoist breaks. Down comes the boom, and there's usually a personnel in the line of this boom either rigging up a load, walking in that area, and it happens so quickly, it's impossible to move. This accident occurred during construction of a 8-story building. The boom hoist broke. You can see on the right-hand side by the lower sheave of the bale how the wire rope is de-reeved through the system. You can see the slack and the break itself. 2 men were killed in this instantaneously. Next, this is a stationary hoist in the marine application in San Diego was deployed and built to handle ships, small ships which are being built, taken out of water, placed in the water after a building, a repair. This is after the accident. You can see the boom hoist line de-reeving through the system. You can see the waviness of the rope and the actual break at the lower center part of the slide. Looking at the upper part, we can see the sheaves which were in this system for boom hoist lines, and below the lower sheaves, you can see the wire rope which is curled, which occurs when wire rope de-reeves through a system under tension. And actually the wire rope break broken in is the lower left section. Total break. And what happens, the break is at one location. It's not a break that extends over a period of length of this rope. It's usually one location which has pre-existing fatigue breaks, internal and external. We'll get into this more, but I just want to point out the importance of inspecting these boom hoist lines because fatalities occur, damage to equipment. Here's an example when that boom actually came down. The gentleman had spent 4 or 5 years building this beautiful yacht. He was a retired admiral. He had planned to travel around the world, and they were lifting this from dry dock into the water. And as it was being lifted, the boat was lifted, the boom was rotated, the boat was then lowered, and at one point, about 20 feet over level of water, it was reported there was a high grinding sound, metal on metal, metal on metal. And finally, there was an explosion, a boom. The boat fell down, bounced in the water, and 2 or 3 seconds later, the boom crushed this boat, beautiful boat. It took 3 or 4 years to replace it, $2 or $3 million, and delayed this admiral's trip by 4 or 5 years. But it happened suddenly and without warning. And again, the wire rope was wearing out, but was never inspected. Again, another photograph showing a broken boom hoist rope. I keep pointing this out because it is so important to inspect and replace these ropes. And as you can see, the position of these sheaves presents a very challenging location for inspection, but it's necessary to do this. In fact, in my latest edition of Bob's Rigging and Crane Handbook, I made note in this that it's so important to check hands-on the boom hoist lines, and also ASME standards are addressing this under the new B30.30, and OSHA has even put out a special request or statement we'll see later on about inspection of boom hoist lines. Now, why do these break? Why do these boom hoist wire ropes break? As I mentioned, if we would outfit and rig a crane, completely operate it and keep operating until something breaks, it's usually the boom hoist wire rope that pulls it to. Why? What's happening? Several things are happening. The wear patterns in the boom hoist wire rope are developed either from drum crushing, bending fatigue, vibration, and impact fatigue. And the impact can not only be from overloading and bouncing the boom, but vibrations which occur constantly through the operation of a crane. And again, these vibrations are dampened within the wire rope. Outer strands, outer wires are actually deflecting, they're moving, they're actually notching one another internally and externally. Next bullet point is corrosion. We're talking about severe corrosion, and you'll see momentarily some photographs and slides of severe corrosion. And lastly, as I emphasized 2 or 3 times, shiv damage. Now currently, there are what they call design factors for different ropes. The running ropes on a crane are mostly a 3.5 or 3.5 design factor. Pennant lines can be 3, but we're going to focus on the running ropes, a 3.5 design factor. I mentioned previously that it's nice to have and appropriate to have good thread winding of the wire rope that's installed under a slight tension to ensure correct operation, and it's important for the operator to continually view these drums to ensure that the wire rope is operating properly, thread winding, and no severe crossover. Picture of a boom hoist drum. It's in a more obscure position. It's smaller in diameter. Its width is less. More difficult to inspect, but it's important for the operator to keep an eye on this. The crossover points always occur on drums. It's always inherent. And these are the points that are usually damaged on a drum on the outer layers when heavier loads are applied. Now, again, I emphasize the point of erratic winding. It can occur very quickly if there's a lack of tension or sudden vibration, impact load, which causes the rope to become out of the thread winding, and then once it comes out, there can be severe damage. Such damage, as you see in this photograph, this was a compacted strand wire rope used as a boom hoist line appropriately, but this was damaged on a drum, damaged when it was not properly thread wound, and on this adjacent upper winding across the drum, this area of damage crossed over a lower section of wire rope, and heavy loading, it deformed it. Even a compacted strand wire rope could not confront this type of damage. Now, kind of elementary, a wire rope, of course, the real advantage of a wire rope is a transfer of tension or loading from one direction to a second. In this case, it can be going over a shiv. When a wire rope operates over a shiv, the inner section of the wire rope, the wires and strands are going into compression. The outer strands are going in tension. And several examples in the past, we've actually painted white stripes around the wire rope circumferentially. And watching these deflect over a shiv or a drum, you can see how the strands move adjacent to one another. Even the wires move within each strand. So that's why it's important to have the right design of wire rope, and especially important to have lubrication throughout its use. I don't want to get too much into engineering. This is a standard formula, and again, I'll make it very simple, that shows what the radial pressure is, and that is, under loading, what pressure is exerted between the wire rope and the shiv or the surface of the drum. And that's represented by the letter P of the unit radial pressure, PSI, or pounds per square inch. It's related to the right side of the equation, twice the tension or load on the rope in pounds, divided by, again, the base diameter of the drum in inches, and the nominal diameter of the wire rope in inches. And if you look at this, just look at the large D. Say we have the same tension, the same wire rope diameter. As this diameter of the shiv or drum, the large D, increases, the pressure goes down. There's less chance of damage. It will increase the fatigue life if larger diameter shivs. As the larger diameter gets smaller, you can see how the radial pressure gets greater, which promotes damage on the drum, damage to the shiv as far as wear, corrugation, and fatigue life of the wire rope. Anyway, this is just kind of a standard formula, but it does point out one thing, that the smaller the diameter shiv, the more pressure on the wire rope and the shiv, and the sooner the wire rope will wear and fatigue. Now, if I could just beg your patience here in looking at this chart. This information came from tests that I was able to actually run in a wire rope laboratory several years ago. At the very bottom, the wire rope that was tested is a 3/4 inch 6 by 25 Pellow wire, right regular lay, EIP, extra improved plow, which is the strength of the rope, IWRC, which is independent wire rope core. It's a steel core. So this construction is a very common design of wire rope that's used on hoist lines, boom hoist lines, pendants. During one production run of one reel, I cut many samples and subjected them to these tests. On the left-hand side, and these were bending fatigue tests, I was able to incorporate 2 different sizes of sheaves. The top 3, I had a smaller diameter sheave, which gave a 15:1 DOD ratio. The last 3 test sample arrangements were a larger sheave. And then in the center column, I adjusted the loads. I wanted to see actually what happens when you vary the load under these conditions. And so I started out with light load of 6,373 pounds, the middle load of over 12,000, almost 13,000 pounds, and the last one, a little over 19,000 pounds, anywhere from design factors of 3 up to around 9. I use these same loading conditions on both a 15:1 and 18:1 DOD ratios. The important part is, let's look at the test cycles on the right. And these tests were conducted over sheaves, bending fatigue, until they met, pardon me, the retirement criteria of 6 broken wires per rope lay, or 3 broken wires per strand. In this case, they all met 6 broken wires in a rope lay, and the broken wires developed, of course, in the areas that were operating over the sheaves. Let me focus on the best condition. If you go down to the 18:1 DOD ratios, the first line will have the lightest loads of 6,373 pounds. This wire rope went over 21,000 cycles before we met the retirement criteria. As we doubled the load on the 18:1, the bending cycles before retirement, around 19,000 was 20,000 pounds. And the larger load of the 18:1 DOD ratio of over 19,000 pounds, a little over 10,000. So you can see in this case, from 6,373 up to about 19,000 pounds, or triple the load, we decreased the fatigue life of the wires by half. What's more dramatic, this 18:1 DOD ratio would represent nominally a hoist line of a crane, whereas a 15:1 DOD ratio above would represent the conditions of a boom hoist wire rope on the sheaves. Reflect with me for a second. On the 15:1 DOD ratio of 6,373 pounds, we went 10,500 cycles before we met the 6 broken wire criteria. That is half. That is half of what we saw with the 18:1 DOD ratio at the same load. It's incredible. So from going to 18:1 to 15:1 DOD ratio, we've decreased fatigue life by half. That's true with the load at 12,746 pounds, as opposed as comparing 15:1 and 18:1. And at the heaviest load of 15:1, the heavy load of 19,000 pounds, we were down to 6,500 cycles before we met criteria based upon wire fatigue breaks. It's incredible. What a difference. This is one condition that boom hoist lines faces, and one reason that boom hoist lines wear out and fatigue sooner. As we look at the cross section of a grooving and within a sheave, or it could be lagging on a drum, there's wear. Of course, sheaves are usually flame hardened. They can be magnesium steel, but the hardness is always less than the hardness of the wire rope. These sheaves can be flame hardened to increase the hardness initially, but eventually the wire rope wears through these hardened conditions. And you can see from a couple slides ago, with a larger pressure, because of smaller diameter sheaves, the sooner we start to wear. This wear actually operates down into a sheave. It can also produce wear accelerated wear, and fatigue brakes. You can see in this slide, this wire rope has been operated in a tight sheave, undersized sheave due to wear. You can see the flattening of the outer wires, the wire breaks that occur, and then as the wire breaks right in the center of the photograph, you can see how they lay over and damage adjacent wires. So once it starts to occur, the rope deteriorates very quickly. So it's important to have these sheaves on size. I mentioned too, you have to look at this photograph for a second. This is a photograph of the grooves of two adjacent sheaves, and you can see right lay rope is used on the upper one, and a left lay rope is used in the lower sheaves. At first, I thought this was a grease imprint, but after cleaning the sheaves, this is a corrugation. These ropes that only had such high pressure, but the sheaves were not inspected, and you can see the imprints of the strands and the wires of the wire rope into the actual base or the grooving of these sheaves. And this condition can easily damage a wire rope within hours. For example, this wire rope is probably operated for about 2 weeks, 2 to 3 weeks on a sheave which had terrible corrugation, very deep corrugation, slightly undersized. In no time, the corrugation produces and focuses on increased pressure. It notches the wire, it cuts the wire, damages it. And once these wires start breaking, they'll damage adjacent wires, and the rope will come apart within, like I say, 2 or 3 weeks. Going back to our boom hoist systems, we can see in this photograph, the upper bale has an equalizer sheave, and not only do the wire ropes fatigue going through sheaves, they will drastically fatigue at the equalizer sheave. Admittedly, if the rope is not moved through the system periodically to distribute the wear pattern, many wire breaks can occur on the sheave, this equalizer sheave. So it's important to inspect that area, plus the sections of wire rope going over these sheaves in the upper and lower bales. During inspection, even daily inspection, I'm really focused and admonishing crane operators, oilers, any inspector at all, to go through the movement of the boom. Prior to operation, wherever the boom location is, lower it several degrees, watch the wire rope as it operates through the sheave, and subsequent photographs will emphasize my opinion on this and give you some detailed information and data, which is important for these inspectors. So during inspection, on a daily basis, move the boom up and down several degrees and inspect the rope going through these sheaves. I also recommend periodically, if it's a 2-drum system where the wire rope going through the equalizer sheave is permanently stationed there, to cut rope and to move this wear pattern through the system. Again, here's a photograph of a upper bale sheave. You can see how remote it is, and it's important to get to that point to inspect the wire rope hands-on. Gotta go back to the basics. I explained what happens when boom hoist ropes fail, why they fail. This photograph, again, came from a laboratory test I conducted many years ago. This piece of wire rope, the section wire rope, is probably 8-10 feet long. We conducted 6 tests, socketed on each end, and then it was subjected not to bending, but to simply impact loading. We had a fluctuating or vibration imparted by a counterweight, and it would impart vibrations. It would load the rope, unload, loaded rope, unload, possibly 100 times per minute. After 40,000 cycles, I removed the rope. And of course, on the outside, as you can see, there's no wear, no broken wires in the outer strands, no crown breaks, lubrication was good. But as I laid or unlaid the strands from the core, focus on the core. Look at what happened. The core is totally fatigued. Pieces of wire, maybe 1 or 1 inches long, looks like shrapnel. It just falls into your hand. Here's a section of wire rope that did not come from the lab, but actual usage in the field. We removed the wire rope after so much service. They were concerned about it because they had a slight decrease in diameter. This rope had been on possibly 2 years as a boom hoist line. We removed it. I unlaid the outer strands, and you can see the same condition. The IWRC or core is totally fatigued. Every wire in that core has broken at least once or twice in each 10 or 12 inch length. Here's a sample of the same wire rope as I unlaid more strands and then actually held onto the core and flexed it. And you can see how the particles, the strands and wires fell out. And in most cases, the wires, each wire was fatigued in many locations. So once we flexed it, these fell out in my hand. It's amazing. Pretty dramatic. And points out the fact that as these boom hoist lines wear out, even boom pennant lines, most of the wear can come from the inside, from the IWRC failing first. Here's a photograph again of a rope that has undergone considerable bending. You can observe there is corrosion between the valleys. You see wear on the outer wires, and you see broken fatigue brakes. These crown brakes are nominal. They're called fatigue brakes. They're on the crown, and they usually are square, right across the diameter and through the cross section of the wire. So again, this is the type of brake you would normally see, normal operations after so many cycles, but you should not see the amount of corrosion we see here. The second rope has been removed. Now, in view of this, we do not see crown brakes. We see broken wires, broken outer wires, which have not occurred on the crowns, but down between the strands. Down between the strands. And if we relocate these wires, these are in the contact point of strand to strand. Each adjacent strand is rubbing against each other. They start to fatigue. And in this case, the core is completely fatigued, no support. And once the core has lost its ability to support the outer strands and provide the spacing between the outer strands during operation, these strands come together, they fatigue, and almost instantaneously the strength of the wire rope drastically and dramatically decreases and can break instantaneously. This photograph, again, is another indication of valley breaks, but in this case, if we would take these long broken wires, we place them in the strands, these wires broke at a contact point against the core. So when we speak of valley breaks in the industry, people will think it's just strand to strand, but it can be strand to core. And
Don, this is Mike. I just wanted to interject here and ask,
yes.
When we have some broken wires and we start to see one or two, whether they're valley breaks or crown wire breaks, I think it's important to relay the volume of adjacent wires that are partially fractured, that are starting to also lose their cross section and also partially fail. And the overall strength of the rope has really dropped off quickly, hasn't it? So it's not just counting whole broken wires, but to also understand that there's likely partial broken wires in the same general area.
Yes, that is true. I think a couple slides from now, Mike, I show a rope that shows just a partial fatigue break or one that has not exposed the ends of the brake. So that's why it's important to run, use a cotton rag to pull across these ropes, because those cotton rags will snag on wires which are almost hidden on the crowns. Yeah. Yes.
Thank you.
Very good point, Mike. Thank you. I want to show you the end of this brake. We've talked about fatigue breaks, which can occur on crowns or in the valleys. This photograph was taken of a wire rope after or subsequent to actually pulling it into an tensile machine. That is, a section of wire rope was socketed, it was placed in a tensile machine, pulled until it ruptured. I cleaned the strands off, placed them underneath the microscope, and took this micro photograph. And you can see at the ends, these are the types of breaks which are evident when a wire rope is simply pulled into. If you look at many of the wires that are tapered down at the very end, almost like placed into a pencil sharpener, these are called tensile breaks. And then you'll have, along with these, in conjunction, what's called shear brakes. These are brakes on the wires that are 45-degree angle. You'll get a combination, tensile and shear brakes occur when a wire rope is pulled in two, mostly tensile. But these brakes I wanted to show you because they are completely different than fatigue brakes, either crown or valley brakes. So kind of get an idea what these look like. Many times during my inspection of broken wire ropes or failure analysis, the first thing we do is clean the wire rope, look at the brake, determine if they're broken tensile, shear, fatigue. That's very important. Now let's go back and look at some valley brakes. This photograph was taken of an actual rope retired from a boom hoist line. They saw one or two breaks, but once the rope was removed, many of these wire breaks that you see here have occurred between the strands, and they were not visible. They actually laid down the strands. They were not visible until the wire rope was flexed. The same thing with this rope. You can see that these square fatigue breaks, once the broken ends are placed back in position, they're occurring at a strand-to-strand contact. And once I start to see strand-to-strand contact breaks or valley breaks, immediately comes to mind there's a good chance, in fact almost 100% chance, that the IWRC or core has fatigued completely, lost its ability to support the other strands, and allowed these strands to abrade and fatigue each other. Once we unlay the strands, they look good from the outside. And again, a photograph, even well lubricated rope, the breaks of the wires are almost completely incomplete in the IWRC. Here's a photograph, and let me go back here. Many times fatigue breaks occur. We don't see any outer fatigue breaks on the outer strands. This is a section of wire rope that was sent to me for analysis, and they said, Don, what is happening here? And I could see maybe one or two or three broken wires in, say, a 4 or 5 length of rope. Good lubrication. So once I was able to take the rope and actually flex it my hand, wow, look what happened. These breaks that occurred in the valley immediately became exposed. They popped up from the surface. Whereas in a straight line configuration of a crane, they were not exposed or obvious, but once they're flexed, they become exposed. Going back to my point, why I recommend inspection of the boom hoist lines by lowering and raising the boom, the wire rope going through these sheaves will be in a flexed position. If there are broken wires that are hidden, they will become exposed on the outside surface of these sheaves, and that is an indication of immediate retirement. And again, it's important to flex these. A couple more samples. This is a compacted strand wire rope. Actually, it was a swedge wire rope that came to me. It had been used again as a boom hoist line. You can see one broken wire in the upper right. In the middle, you see a fatigue break. Mike mentioned momentarily a minute ago. So these breaks occur, and they're very hard to detect. They start to break on the left-hand section, right in the middle of the rope. The one bright wire, you can see there's a partial fatigue break. It's very hard to see until it's cleaned. So I have this sample. What do I do with it? I flex it. Incredible. Look at the number of breaks that were existing that were not obvious in a straight line configuration. So not only do I recommend during inspection on these daily inspection to lower and raise the boom to expose these wires at the sheave location, it's important, to evaluate this wire rope from its initial condition to the final condition, not with broken wires, but again with rope diameter. And I'll delve into that more in just a moment. Here's a strand taken apart. It was flexed, and as I actually removed the strand, these wire sections fell out. All fatigue breaks due to bending or impact fatigue. Another location, higher magnification, you can see many of the breaks will be exposed and popped up. Again, as Mike mentioned, in the very center, there's a wire that partially fatigued and then it's pointed. Has a very sharp, like it's peeled off. That wire has fatigue probably halfway through the wire, and once I flexed it, it broke off the rest of the diameter or cross section of the wire. So this type of break in a long section, straight section, would not be obvious. But once it's flexed, it becomes very obvious. Let me focus now on the problem of severe corrosion. This is a photograph of a rope that I was able to take most of the lubrication off the outside. And once it was exposed, you can see the wires are heavily corroded. It almost looks like the surface of the moon. It's pitted, they're corroded, and once the wire is pitted to this point, it should be immediately, if not sooner, replaced. These pits cause what we call notch risers, or they're notch sensitivity risers, and will lead to fatigue breaks. It's like notching a wire with a file and flexing it, it'll break. These pits from corrosion serve the same purpose. You can see on the outer surface, look at the corrosion between the valleys. It's a very dark, very penetrating, very corrosive element, and we see the wires that can start break up very soon in fatigue and bending if this condition is not remedied. Here's a wire rope. You can see some wire fatigue breaks, and again, right in the middle toward the top, there's some partial fatigue breaks. Magnification and cleaning, you can see them, but normally you would not. So the rope was retired because of this, the breaks. But note also the corrosion in the valleys. It's a dark red rouge that comes out from the rope itself. Now, normal rope, of course, being steel, if there's a light red rouge, it can be wiped off with a rag. There's no pitting. These can be relubricated and used, but not in this case. Sample. This wire rope was used in the oil field where heavy black asphaltic-based lubricant is used. And of course, they like to reapply the same type of lubricant. And what happens, not only does it cover the wire rope, so it's very difficult to inspect, the heavy black lubricant does not penetrate down between the strands nor to the IWRC. So once this wire rope was exposed and cleaned, you can see that there are sections that are bright. That's on the outer layers where this black lubricant was. It was just a cover, it wasn't a lubricant. The very top part of the photograph, very interesting. That's the IWRC. To the left was an area that had not lost its lubrication. To the right, it was exposed to acidic or caustic environments, which took the lubrication off, and being relubricated did no good. So you can see when internal damage can occur, even when the outside is lubricated with the improper lubrication that does not penetrate to the core and between the strands. One area of inspection of a wire rope is to look for an increase in lay. Now, I have not seen more than 2 or 3 cases over the years that has a drastic or dramatic increase in lay. This wire rope not only has been fatigued, the wires of the IWRC have actually come out from between the strands. I'm not sure of the actual application, but I don't see this too often. If it becomes quite obvious, the link visually, then it should be replaced. Diameter reduction. Let me refocus again. Manufacturers of wire rope can produce a wire rope and design it to be 5% over nominal down to 0. For example, a 1-inch wire rope can be made to the actual diameter of 1.00 or 1.05 inches. So it's important to know what the initial diameter is of the rope so that it can be compared to subsequent diameter measurements as the rope is being used or an application. So that 5% reduction should be based upon the actual diameter of the rope and not nominal. So that's one area we're focusing on. Hopefully we can address that in the future. Here we are, back to the inspection criteria. We talked about the randomly distributed buccal wires. Be very careful on boom hoist. If you see lots of crown breaks, it should be replaced. As we go down to the third bullet, 1 outer buccal wire in the valley at the contact point of the core. 1 buccal wire that's obvious, but as you saw, the rope is replaced or as it's flexed over a sheave, we see many broken wires that are actually in existence that are not obvious. Where 1/3 the original diameter of the outer individual wires, again, I like to go back to basing the actual diameter of the rope on the crane as opposed to the measured diameter to give us an evaluation of the actual wear. And of course, physical damage, the heat damage I briefly mentioned, a reduction in nominal diameter of 5%, and again, I emphasize that 5% reduction should be based upon the actual diameter of the rope as installed in that particular crane. In standing ropes, and again, these are pennant lines, we talk about broken wires in the valley should be replaced, and broken wires at the end connection. And lastly, the severe corrosion we saw in some of the photographs that actually cause early fatigue breaks, loss of cross-section of seal area, and which could lead to a very immediate broken wire rope. The last OSHA regulations that came out address inspections for wire rope, and this is an overall view, but let me focus on a couple of areas that I've highlighted in yellow. First of all, the upper left. Rope lubricants that hinder inspection must not be used. What that refers to is the lubricant which is applied in manufacturing and also in the field must be such that you can still observe broken wires or damage to the rope structure. Should not be a lubricant which is black asphaltic base which covers the surface, or any type of lubricant which covers the surface should not be used. Under shift inspection, a competent person must conduct a visual inspection of the wire rope prior to each shift. And I look at this, okay, we inspect it, we get up there in the boom hoist line, if we have to measure diameters, we use a cotton cloth to look for broken wires, and we operate that boom to several degrees with an oiler observing the wire rope as it flexes over these sheaves. Going on down to the critical review items, we can see it. Particular attention must be given to the second bullet. Wire rope being used for boom hoist lines and luffing lines, particularly at reverse bends. Reverse bends will cause fatiguing at a much more rapid rate than bends in the same direction. The last bullet, wire rope in contact with saddles, equalizer sheaves, or other sheaves where wire rope is limited in travel. Lastly, I'd like to go to the center column under annual comprehensive inspections. Toward the very bottom, we're highlighted in yellow, wire rope subject to reverse bends and wire rope passing over sheaves. And it's so important, especially with boom hoist lines. I really thank all of you for attending. I hope the information has been very valuable to you. I've presented it several times. This article is also published in Sling Makers from AWRF in the 2013 fall issue. So reprints are available through them, or you can contact Mike at ITI and they can provide more information. But again, I thank you for this, and I'm willing to take questions at this time.
Okay, Christina, do we have any questions in from any attendees today?
Yes, we do. The first question comes from William, and he's asking, how often should you change out boom or hoist line if it's not damaged?
The inspection criteria is important. There's no way to put a time limitation on wire rope retirement. It's based on visual inspection, and so I go back to a more thorough inspection on a daily basis, and especially a documented inspection report monthly and yearly. But the more
so
you...
there's no time calendar, Don. It's really about what's the visual inspection telling us and the condition of the rope, metal loss, and any potential broken wires we can see and or corrosion. So it's really based on visual, right?
It's based on visual and actual diameter measurement, yes, and use of a cotton cloth or a cloth that will detect broken wires. So we cannot put a calendar or a time limitation, but the more, for example, the heavier the operation, the more vibration, the more critical or it is to inspect daily and more detailed daily. If, for example, if you're getting like a pile driving, or if there's a crane subjected to overloading or lots of vibration, again, know that these wire ropes on boom hose lines are going to exhibit wear and fatigue breaks sooner.
Don, if I can interject something here, we had a situation where a crane was set up it was close to the building operation, but their staging area was a pretty good distance away. And so they were regularly booming down to a 20 to 30 degree boom angle and picking up items over here in the staging area, and then they needed to swing around and boom up to work on the building that they were assisting with. So this repetitive boom down to 20, swing around, boom up to 70, boom back down to 20 and up to 70. So it was a very high, severe working condition, and we had a serious a failure and a double fatality involved. And I think that's the kind of thing you're really talking about, is what some of your operating conditions are going to dictate to some of the maybe the more focused and frequent inspections and where you're going to be looking for the damage.
It is, and again, as you mentioned, the more severe operations and multiple lifts, the frequency of booming up and down, plus you'll watch a boom, during operation, picking, rotating, lifting, you'll see the boom flexing. You see the boom flexing. So it's not only a matter of the bending fatigue in the shivs, it's a matter of these flexing operations that produce impact and vibration throughout the lines, and these produce fatigue breaks internally.
Yep. Okay, excellent. Go ahead, Christina, if you got any more.
I do. The next question is from Sue. How critical is it with millimeter ropes versus standard rope for going through the shivs? The example given is a 19 millimeter versus a 3/4 inch compacted type wire rope.
Good question. There's been what they call a soft conversion of shivs, and shivs are still not manufactured exactly to size. These shivs are mostly manufactured at least 2.5% over nominal, knowing that wire ropes can be 5% over or down to 0% over nominal. So the shiv manufacturers are trying to accommodate a range of sizes, and so to date, it's been fairly successful as far as using the soft conversion of comparing millimeters to actual inches. So as we go through this, the main thing is, if I see a shiv, I would like to see a shiv. If it has to be slightly over the nominal diameter, is much better than slightly below. And again, it gets back to actually measuring the shiv grooves to make sure it properly fits. And that's all I can say on that condition. I would go back to the shiv manufacturers and indicate to them, or the crane manufacturers, if we use these ropes, ask them their experience or any testing data they've done.
Don, ideally, we would, if we were going to have a long-term application and make that decision to switch from imperial to metric, we would probably then decide to go ahead and switch the shivs over accordingly, right?
If we switch from imperial to metric, universally, the shivs should also follow. Yes.
Okay, excellent. All right, Christina?
Okay, how often should you oil rope and what should you use?
That's a very good question. I'm glad that was brought up. When you say oil, I don't like to use it. I say lubricate. And the reason I'm saying a wire rope lubricant should be used. Many oils will contain sulfur or additives or components which are detrimental to steel. So a wire rope lubricant, which is highly penetrating, these are mostly petrolatum, they can be wax-based. Many of these have a solvent cutback, which are biodegradable, which allows the lubricant to be applied usually and most properly at a drum or over a shiv where these wire ropes travel. If you'll observe a wire rope being flexed, on the outer sections, the strands actually open slightly, gives you more space where the lubricant can penetrate. This can be applied by either dripping, it can be a spray, it can be applied by a rag, but what I see mostly is it can be sprayed on or dripped on, allowed to remain for maybe 15, 20 seconds, and then the outer surface can be lightly wiped to prevent accumulation or drippage on the machine. And once the lubricant is applied, make sure it penetrates, it has a solvent cutback, and then it will harden and become less liquid. And
so the strands open up a little bit, Don, on the
sorry?
shiv breakover. The strands open up a little bit on the shiv breakover, so that's a good place to lubricate.
Right, it opens up more space, so more lubrication can penetrate. We know we're not going to get the wire rope lubricant down to the center of the strands, but it will penetrate between the strands down to the IWRC, and at least get a good lubrication between the outer strands and the core itself.
Sure. Okay. Excellent. Okay. Any more, Christina?
Yes, I've got a question from Paul. Has there been any research into using sensing devices and/or electronically sensing for potential wire rope failure before failure occurs?
Is this referring to non-destructive testing, or I mean, like, are they talking X-ray testing?
You know, Don, I think it's about the ability to detect broken wires of ropes in service on machine, any sensing of wire breaks in
Okay, thank you.
from contact point to contact point.
There are pieces of equipment from various manufacturers that can be installed. Most of these are based upon what they call a magnetic flux reflection or X-rays. But these devices, which I've seen, are quite bulky, they're heavy, they're expensive, and they're not that effective on a continually operating wire rope. I know they've been used on mine shaft ropes, other various applications, possibly ski ropes, where they can be installed permanently and the rope is going to last for some time. And this gets back to using such equipment. For example, it's magnetic flux, where it goes through a chamber of magnetism or electronic flux, and a chart readout will show blips. I kind of compare this to a heart monitor. You see blips, and this is recording differences in wire diameters, spacing between wires and strands. But you have to there has to be a baseline, and so you have to be comparison. So the bottom line is I've seen nothing effective for crane ropes at this point.
And there's nothing in line with the rope that would be able to detect anything. So there's no.
Not to my knowledge, it's effective and efficient.
Right.
No.
Right. Okay. Good question. All right. Well, we're going to need to wrap it up. If there's other questions, Christina will get them tabulated or sent to me, and I'll get them distributed to Don. Hopefully, we've got your emails with those questions.
Yes, I'd be glad to answer those.
I'd like to try to respond to you. We sure appreciate very much the participation today. And Don, thank you very much for the great presentation and the super information that you've provided for us. So we want to thank everyone for attending, and hope that they're having a good summer, and we'll be able to see you on a future webinar. And Don, we'd sure like to have you back in the future.
Thank you, Mike.
Some more subjects on wire rope would be great.
I'd be happy to do that. And thanks to all the participants, and thank you, Mike.
Okay. All right, Christina, why don't you go ahead and sign us off, and then we will wish everyone well.
Will do. Take care, everyone.
Okay. Bye-bye.